In this circle, from the origin, or from the centre, sorry, we've got two radii. We've got one here and one here. And they both meet the tangents at 90 degrees, as we were talking about before. So we know that the lines OP and OR are equal because they're both a radius. And the tangents come out here and meet at point T. Another interesting fact is that PT equals RT. So this length is equal to this length, and we've got ourselves a kite. And it also means that the triangles TPO, so that's TPO, the top one, is congruent to the triangle at the bottom. So congruent means that they are identical in every way, except it's just a mirror image. So the lines are the same length and the angles are the same size. So let's have a look further down here. We've got another theorem to think about. If we were to draw any sort of triangle inside a circle, we could call it a cyclic triangle. Let's call it PQR. An interesting fact is if you draw a tangent at P, then the angle that you're making here with that tangent is the same as the angle the other side here. And this is known as the alternate segment theorem. And it's a bit of an odd one because just looking at this, it's not very clear. I mean, we could draw it maybe with a different colour. Let's say yellow. We could do it the other side. So this angle here, that would therefore be equal to this one here as well. And there's quite a nice proof for that, which I'm going to go through now. The proof for circle theorems is it's important to be able to show theorems clearly, to prove theorems clearly, because sometimes it asks to explain how you've got an angle, and this is the right format to use. First of all, if you construct the diameter POS, so I should do this in a different colour. I don't think I need to change my layer though. Right. Okay, we're back. So I'm going to draw the line POS, and because it goes through the diameter, through the centre rather, this is called a diameter, and it means then that if I were to draw any sort of triangle coming from that or subtending from this, let's say it goes to R, we know from another circle theorem that we talked about before that this must be a right angle, and that's what it says here. Angle SRP is 90 degrees. Well, what now? The angle PSR, so PSR, this one at the top here, is equal to angle PQR. So PQR is here. Now why are they equal? Because they both subtend from the chord PR. So from PR, I should do that again. We got two triangles here subtending from the chord PR, and we know that these two angles here are equal. So this has now created any sort of random triangle inside our circle, and they've called that angle X. So angle SPR must be then 180 degrees minus X minus 90. So this angle here, we could write that also as, well, if I were to write 180 degrees minus 90 minus X, then that is equivalent to saying this. It's 90 minus X at the bottom there. So the angle RPT, so that's R to P to T. Now where is T? Over here. Now why are they using that triangle? Why are they using this angle? Well, because to show that the alternate segment theorem is true, we've got to show that this angle here is the same as this one here. And that angle there can be found from looking at the angle from SPT and then subtracting what we've just worked out. But from what we talked about before, we know that if we have a radius meeting a tangent, that's always 90 degrees. So in a different colour, I'm going to choose the red, we know that this angle here is 90 degrees. So if we did then 90 degrees and minus this thing, minus in brackets 90 minus x, then 90 minus 90 is 0, and then minus minus x is x. And that has shown that this angle must be x, which is the same as that one up there. And that means that the alternate segment theorem has been proved. Interesting, huh?